Okay, hello. Welcome to the Chapter 6 review for statistics. Sorry for a bit of a late start here. Had some tech issues, accidentally shut down my docking station. Anyway, so as usual, we are recording this and I will be emailing out the link to the recording to everyone who has provided me their email address in the past. If you want me to send you previous recordings that you didn't attend, just let me know. I've put my email in the chat, maxine.horn@datonastate.edu, or you can email brandy.horn@datonastate.edu. Both will come to me. Brandy is my first name. I go by Maxine, my middle name. I know it's confusing. All right, so let's dive in. So when I send out the link to the recording, I will be also attaching a PDF of I'm calling it like a study sheet, but it is essentially just like some reference pages that kind of break down everything that you guys are going to need to know and know how to do for this chapter. So let's walk through it. It's only 3 pages, and then we'll dive into the problems themselves. So we're talking about confidence intervals in this chapter, right? So, sorry, let me get my calculator here. So the first thing is when we talk about confidence levels, I just had to give one as an example. So I did a 95% confidence level. So that means that the area in the center is 95%, right? Because remember, the area under the whole curve is 1. So the area in the center is that 0.95 or 95%. So the remaining area in the two tails together is what's called alpha. Okay, so that's going to be 1 minus whatever your confidence level is. So in this case, 1 minus 95% is 5% or 0.05. But then we have, so that's each of those tails together is alpha. Each of the tails individually is going to be half of alpha, right? Because there's 2 tails. So both of them together is alpha. Each of them individually is alpha halves. So you take your alpha and you divide it by 2. So that would be 2.5% or 0.025. Okay, so keep that in mind as we talk about finding our z-scores or our t-scores, that this is the relationship between our confidence level and all of this alpha stuff, right? Okay, so another thing that you're going to be doing in this chapter is finding a sample size. So we have a few different situations where you're doing that. Either you're dealing with like population standard deviations, either knowing it or not knowing it, or you're dealing with proportions. Okay, 2 different types of problems here. So as with a lot of things in stats, you have one way to do it if you know your population standard deviation, and you have another way to do it if you don't know your population standard deviation. Okay, so you're going to need to know this formula, right? That your sample size is equal to your z alpha halves times your population standard deviation over your margin of error, all to the 2nd power. If you don't know your population standard deviation, you can estimate it using your sample standard deviation, as long as there was a preliminary random sample with the sample size being greater than or equal to 30. So like if there was a previous study that can give you some information about it, then you can use your sample standard deviation rather than your population standard deviation there. For proportions, when you know your population proportion, right, that's what p hat is, the population proportion, then your sample size is going to be p hat times q hat times your z-score, your z alpha halves, over your margin of error squared. If you don't know p hat, then you can assume it's 0.5. And remember, and I have this written elsewhere on the sheet, but remember that if you have p hat, you can find q hat because it's just the complement of p hat, right? So you do 1 minus p hat to get q hat. So if we have to assume that p hat is 0.5, if we don't have it, we assume it's 0.5, then that means by default that q hat is also 0.5. which means that this whole thing right here becomes 0.25. So you might see that formula as well. But if you don't want to have to rely on memorizing one more formula, then don't worry about memorizing that. Just know that if you don't know p hat, you can assume that it's 0.5. Okay. All right. So now let's talk about the elements of confidence intervals. So again, as with a lot of things in statistics, we have when we know our population standard deviation, when we don't know our population standard deviation, and when we're talking not about means, but about proportions. Okay, so each column talks about the three different scenarios. So quick recap, p hat is your x over your n. Okay, so reminding you of the symbols here. So some of these should already be familiar to you. You've used them in previous chapters. X bar is your sample mean, n is your sample size, and sigma is your population standard deviation. So S is your sample standard deviation. And over here we have p hat is the sample proportion of successes. Q hat is its complement, which is the sample proportion of failures. There's that relationship again. Q hat is 1 minus p hat, and n, like the others, is your sample size. So when you're dealing with your population mean, when you know your population standard deviation, we use a z-score, a z-alpha halves. But when we don't know it, we use a t-score, which is new in this chapter. Okay, so we use t-alpha halves. For proportions, we use z, same as with the mean. All right, so then the formula for error. Okay, so this is the error. We have three different formulas. Again, you'll need to know these formulas. So it's either z alpha halves times population standard deviation over the square root of the sample size, or t alpha halves instead of z alpha halves, your sample standard deviation rather than your population standard deviation over the square root of your sample size. And then with proportions, we have a different formula, our z alpha halves times the square root of p hat times q hat over the sample size. Okay, so then we have different ways that we can write our confidence interval. So if we have, if we're talking about the means, then we're saying that the true population mean falls somewhere in between, and then you're creating a number here, right? You're putting whatever your sample mean was minus your margin of error, and your sample mean plus your margin of error. Right, so it's the same thing for both of these. And then here, we're not talking about means, we're talking about proportions. So we have the true population proportion. I think I was calling that population before, sorry. The true population proportion is your sample proportion minus your error, and your sample proportion plus your error. So quick reminder that even though this might look confusing the first time you look at it, you probably have heard this talked about in sort of everyday life, or maybe if you've ever taken, I don't know, like a science class where you say like, or not even that. If somebody said like, oh, I'm 90% sure of something. Oh, you can't see that, plus or minus 5%, right? You've heard that like, oh, plus or minus 5%. Well, that means that you take 90, whoops, not 99, 90, and you can either add 5% and you can subtract 5%. So that's going to be 85 and that's going to be 95. So if we say 90 plus or minus 5%, we're saying that the thing, whatever it is somewhere in between 85 and 95, right? So sorry, you can't see that. Somewhere between 85 and 95. So that's really all we're doing here, just with more complicated things. Okay, and then we do have specific requirements for when to use each of these situations. You use this, right? You use this formula when your population standard deviation is known. You use this one when it's unknown. And then for both of them, you need to have a simple random sample, and you need to do one of two things. Either it has to be normally distributed, or if it's not normally distributed, that's okay, as long as your sample size is greater than 30. And then the other way around as well. If your sample size is not greater than or equal to 30, that's okay, as long as it's normally distributed. So it can be either one of those things, but it has to be one of them. It can't be neither of them. And then for proportions, our requirements are that we need to know, or I'm sorry, our population standard deviation is unknown. We only have two independent outcomes, right? This is binomial, and that both n times p hat and n times q hat are greater than or equal to 5. Okay. All right. So now we get into, okay, how do we actually find these things? Okay. So here, let me zoom this out a little bit. I feel like we need to be able to see the whole page. So how do we actually find these? So sometimes you're going to be asked for the confidence interval, and you can do it by hand, or you can do it in the calculator. Here are the three different scenarios that we talked about before: when we know our population standard deviation, when we don't know it, and then when we have a proportion. So here's how you do that in the calculator. Here's how you do it by hand. We'll go through this in more detail. But sometimes, instead of asking you for the final, oh, give us the full confidence interval, sometimes you just need to find your z-score or your t-score, your z alpha halves, your t alpha halves. So again, those can either be done by hand or they can be done in the calculator. Okay. So I'm not going to go into a bunch of detail here on this. We will just refer back to this as we go through the problems. Okay. But again, this is going to be provided when I email out the link to the review. Okay, so let's get started. So get my sheet over here. The grade point average collected from a random sample of 150 students produced a mean of 2.86. Assume that the population standard deviation is 0.78. Construct the confidence interval for the population mean. If C, your confidence level, is 0.98. Okay, so there was a bunch of things that they just sort of wrote out for us. So let's go through and let's start labeling things, okay? So a random sample of 150 students, well, that's our N, right? That sample produced a mean of 2.86. Okay, that's an X bar. Sample mean. Assume that the population standard deviation is 0.78. Okay, so that's sigma, population standard deviation, 0.78. Construct a confidence interval for the population mean. If you're C, I always like to write CL. Back in my day when we were in school, that's what we called it, CL, confidence level, is 98% or 0.98. Okay, and they want us to construct the confidence interval. So let's start by doing it by hand, okay? So we're going to do it both ways. We're going to do it by hand and we're going to do it in the calculator. So when we do it by hand, the first thing we have to do is we have to calculate our either the z-score or the t-score, because that is required to plug into our formula to find the error. And then once we have the error, then we can add and subtract it in order to create the confidence interval. Because remember, this is what we're trying to create, right? We're trying to create this interval. So we need an X bar and we need an E. So we need to use this formula to find E. Okay, well, we can't do this formula unless we have either the T or the Z, depending on which situation we have, right? So that's why we're starting with the Z or the T, because we need it to find the E and we need the E to find the interval, okay? All right, so let's determine which of these three situations we have. We were given a population standard deviation, so that means we are in this first column here, okay? So the first step is that we need to calculate our z-score, not t-score, but for this one it's z-score. Okay, we need to calculate our z-score. So how do we do that? Because again, we're going to do this fully by hand first, and then we're going to do it in the calculator. Okay, so for the z-score, even for this, we could find the z-score in the calculator, but for right now, we're going to find it by hand. Okay, so if the confidence level isn't shown in the critical values table, well, let's check and see if it is in the critical values table. So in your book, or if you're, if you have access to the book online, it's going to be probably not, the same page, but in the back of the textbook, there's all these tables, appendices, right? There is I'm trying to get to the right one here. You've got you've seen this before, right? We've used this a lot, finding z-scores, finding the area to the right and the left of a z-score. And then down at the bottom of the page, got a lot of wires here I'm working around, is a little table of critical values. So what they've done is they've said, hey, if you're doing confidence intervals, we've gathered some of the most commonly used confidence levels, and we've just gone ahead and given you your z-score. Okay, so if you have 0.8, 0.9, 95, or 0.99, then you don't have to go look it up in the body of the table because it's right here. They give it to you right here. Okay, so ours was 98%. Well, unfortunately, 98% is not here. Okay, that's okay. We can still find it. It just means it's going to take just a little bit of extra work. So the confidence level isn't shown in the critical values table. I gotta zoom this out again. I feel like this can't see the whole page here. Okay, so the first thing we have to do is find the alpha halves and then look that area up in the body of the table and make sure to use the positive value. Okay, so when in doubt, draw a picture, right? So if I have a 98% confidence level, that means that the area in the center is 0.98. Okay, so that means that my alpha is 1 minus 0.98. So my alpha is going to be 0.02. So that means together, both of these tails are 0.02. So that means that one tail individually, or half of alpha, is 0.01, right? Each of these tails is, alpha halves is 0.01. Okay, all right, so we just found alpha halves, which also, if instead of reasoning through it, if you just want to say, well, what's the formula? Well, you do 1 minus your confidence level divided by 2. So 1 minus 0.98 divided by 2, 0.02 divided by 2, that's 0.01. So to me, it makes more sense to do it this way because you're reasoning through, you're understanding what's happening, but you can also just do it this way, just to get the number. All right, so we have our alpha halves, it's 0.01. We're now going to look that area up in the body of the table to find the corresponding z-score. So I'm going to look for 0.01 in the body of the table. Right, so let's see, where is that? So, okay, so I've got 0.0099 and 0.0102. So I can think of this as, this is like 2 away and this is 1 away. So this one is the closest one, right? So I say, okay, I've got negative 2.33. That's going to be as close as I can get to 0.01. But I don't want to take a negative 2.33. I need to make sure to take whatever value I got and make it positive. So my z alpha halves is going to be positive 2.33. All right, so we calculated our z alpha halves. Now that we have our z alpha halves, we're going to plug it into our error formula. Okay, so again, going back to our formulas, we found our z alpha halves. Now we're going to plug it into our error formula. So our error formula is z alpha halves times population standard deviation over the square root of n. So let's plug in what we know. Z alpha halves was 2.33. Our population standard deviation, they told us, was 0.78. And our N, our sample size, is 150. Okay. All right, so in the calculator, 2.33 times 0.78 divided by the square root of 150, and we get our error is 0. Let's see, I'm gonna go to 3 decimals here, and then I'll go to 2 at the final answer. So, all right, great. We have our margin of error. Okay, right, plus or minus that margin of error. Now we need to add and subtract it from our sample statistic to create the confidence interval. Right? We're adding and subtracting it from our sample statistic to create the confidence interval. So we have that our mean, our true population mean, is somewhere between our sample size, our sample mean plus the error and the sample mean minus the error. So our sample mean was 2.86. We found our margin of error was 0.148. So again, in the calculator, and I'm going to go to 2 decimals because the answer was rounded to 2 decimals here. And then okay, so interpreting this, we're saying that we can say with 90% confidence that the true population mean is between 2.71 and 3.01. Okay. All right. So we did all that work to get our confidence interval. It's important that you guys know that this can be done by hand and that it has been done by hand plenty of times, right? But also, when you are taking the test, you can do everything we just did, but in the calculator. I mean, you can find the confidence interval, but just in the calculator. So let's go down to here. So we're finding the confidence interval. We did it by hand. Now let's do it in the calculator. So again, we've got our 3 different scenarios. Either our population standard deviation is known, or it's unknown, or we're dealing with a proportion. So here it was known. Okay, so what are we going to do? We're going to go to stat, right? Stat button. We're going to arrow over to tests, and we're going to go down to number 7, which is Z interval. Okay. This is a confidence interval, and it's using a Z-score, so Z interval. We want to make sure that we've highlighted the word stats. You don't want to do data. Your calculator might default to data. Make sure that you arrow over to stats and hit enter so that stats is highlighted. Okay, then you're going to go in and you're just going to plug in your values. You're going to plug in everything that you were given, right? Okay, so let's go back to what we were given. We wrote it all down at the beginning. Okay, so the first thing it asks for is population standard deviation. That's 0.78. Then it asks for the sample mean, 2.86. Then it asks for our N, our sample size, that's 150. And the last thing it asks for is our confidence level, which is 0.98. So we're going to go down and we're going to hit calculate, and there it is, 2.71, 3.01 if we round to 2 decimals. So you can see the amount of work that it took to get the confidence interval in the calculator versus the amount of work it took to get it by hand. So I want to go back real quick to when we were doing it by hand. Our first step here, when we found our Z alpha halves, when we looked it up in the back of the book, I just want to draw your attention to, if for some reason you do need to find just specifically your Z alpha halves, you can absolutely do it by hand, but you can also do it in the calculator. right? So the way that we would do that is we would go second vars. So second vars. And the reason that it's second is because we actually want distribution up here. And then you're going to go down to number 3, inverse norm, right? Okay, your area is your confidence level. Our confidence level was 0.98. You want to leave your mean and your standard deviation is 0 and 1 so that we can get a z-score. And you have to make sure that for the tail that you tell it that this is the center. You have to do that, okay? And then you paste it in and it gives you both your negative z-score and your positive z-score. Because remember, what it's telling you is the z-scores that correspond to these right here, right? The z-score right here and the z-score here. Now, when we're doing confidence intervals, we always take the positive z-score. So you would look at this and you would say, okay, I have negative 2.33 if I go to 2 decimals, and I have positive 2.33. So I'm just going to take the positive one. Okay, so you can also do that portion of this. If you wanted to do the rest of this by hand, but just find the z-score in the calculator, you can do that as well. Right, so there's kind of like 3 levels here. So you can do it fully by hand. You can do it mostly by hand, but find your z-score in the calculator, or you can do the whole thing in the calculator. Okay, so as we go through, I might be doing some of them by hand. I might be doing some of them in the calculator. It depends on what we've got. And it depends on our time, because I don't want this to go for too terribly long. All right. So my pen has run out of lead, even though I could have sworn I just put more in it yesterday. So give me just a moment. And actually, while I'm doing this, why don't you read through this problem and see if you can label what all of the things we were given are, right? Because that's our first step. Read through and label. Okay. So in a sample of 10 randomly selected women, it was found that their mean height was 63.4 inches. From previous studies, it can be assumed that the population standard deviation, sigma, is 2.4, and that the population of height measurements is normally distributed. Construct the 95% confidence interval for the population mean. Okay, so in a sample of 10 randomly selected women, that's our N. N is our sample size, 10. It was found that their mean height, so the mean in that sample, is 63.4. Okay, from previous studies, it can be assumed that the population standard deviation, so sigma, is 2.4, and that it's normally distributed. So let's talk about that real quick. Remember our requirements? Right, so our requirements is that we need to know our population standard deviation. Okay, we do. Well, either we know it or we don't. In this case, we do, so we're in this column. It needs to be a simple random sample. Yeah, it's random. Excuse me. And we need to check one of these boxes. Either we need to be normally distributed or our sample size has to be greater than 30. Now, in the last one, that wasn't a problem. Our sample size was 150. That's definitely 30 or greater. But here, our sample size is only 10, which would create a problem, except for the fact that we have met this requirement, right? It's either one of these, but it has to be one of them. It's okay that our sample size is super small because it's normally distributed. It's got to be one or the other. So that's why they've specified that, because you have to make sure that it's one or the other. Okay. So, I mean, in the real world, if you don't have one of those things, then you just can't calculate it, right? You're not able to draw any meaningful conclusions because this doesn't apply if it doesn't meet one of those requirements. Okay. So, okay, construct the 95% confidence interval. So that's our confidence level is 95%, 0.95, for the population mean. Okay, so we want to construct a confidence interval, and we know our population standard deviation. We're going to construct a confidence interval. I'm going to do it in the calculator. We know our population standard deviation. So we're going to be doing stat test z interval and plug everything in. Okay. So in my calculator, I'm going to stat, right, this button right here, stat, arrow over to test, and I can either arrow to the right twice, or I can arrow to the left and it like goes back around, right? So I'm going to arrow to the left. That's one less button I have to press. And then we go down to number 7. I can either arrow down to 7, or I can just press, you can't see that, I can just press number 7 and it'll just select it, right? So Z interval. And we're going to put in all of our information. Okay, population standard deviation, that's 2.4. Sample mean is 63.4. N is just 10. And our confidence level, we want to be 95% confident. And there it is. And the answers have been rounded to 1 decimal. So we'll take these answers and round to 1 decimal. I always do a quick refresher on rounding rules, because you never want to get something wrong because you rounded wrong. If you are told to round to 1 decimal, you underline the place that you're rounding to. You look to the number to the right. You say, is this number 5 or more? If so, the number I've underlined goes up 1. If it's not 5 or more, so if it's 4 or less, the number underlined stays the same. This is 5 or more, so this goes up 1. So this becomes 64.9. Okay. That's all there is to it. Okay, number 3. A nurse at a local hospital is interested in estimating the birth weight of infants. How large a sample size must she select if she desires to be 99% confident that the true mean is within 2 ounces of the sample mean? The population standard deviation of the birth weights is known to be 7 ounces. Okay, so we're being asked to say how large of a sample size we need to have. So we go back to our formulas, which we need to know, right? Finding sample size. And we don't have a proportion here. We're dealing with these. So our N is going to be our Z alpha halves times our population standard deviation over our margin of error squared. I'm going to rewrite that formula up here real quick, just so that we have access to that. Okay. And let's go ahead and start labeling everything that they've given us, okay? She wants to be 99% confident. That's our confidence level. Is within 2 ounces. That is our margin of error, okay? The population standard deviation is known to be 7 ounces. Okay, so we look at that and we say, okay, great, except we aren't given everything that we need to plug into this, right? We're not given a Z alpha halves, we're given a confidence level. But just like before we got our Z alpha halves based on our confidence level, we're going to do that again, okay? So that's why we have in our sheet here how to find your Z-score or your T-score either by hand or in the calculator. So I'll do this one more time by hand and in the calculator. So if our confidence level is 99%, what we're saying is that the area in the center is 0.99. So our alpha is 1 minus 0.99, so 0.01. So the area in each individual tail is alpha halves, which is half of alpha, right? 0.01 divided by 2, so 0.005. Okay. So then we're going to, well, this is if we were doing, if it wasn't in the in the back here. So I'm pretending like it's not. I think it is. I think that's a common one. So we're looking for 0.005, and it's directly in between this and this, right? So we have 2.5, and then we're directly in between 0.07 and 0.08. So that's going to be 0.075. So it's 2.575, right? You see that? See, it's halfway in between there and there. Halfway in between here and here is 0.075, 2.575, okay? Or confidence level of 99, 2.575, right? Some common ones are here. You're not always going to have yours here, but if it is there, great. It saves you that trouble. Okay, so we got that our Z alpha halves is 2.575. And again, we always use the positive value when we're doing these confidence intervals, right? Now, if I were to have done that in the calculator, so if I need to find my Z alpha halves, which you do when you're finding your sample size, you could also do it in the calculator. We're going to do second vars. We're going to go to 3. I'm just going to hit 3. And your confidence level is your area. You leave your mean and your standard deviation as 0 and 1, and you make sure that it's marked as center. And then it's going to give you your negative and your positive, and you just need to make sure that you're using the positive. Now, for rounding here, you'll notice that this could be a little bit different, right? So the numbers in the table have been rounded a little bit. So if you're going to 3 decimal places, that would be 576. So you can see the difference there. But it shouldn't be enough that you're getting a completely different answer, right? Okay, so now we have everything we need. So let's go ahead and plug these things in to our formula. So we have our Z alpha halves is 2.575. Our population standard deviation is 7. And our margin of error is 2. And we are taking that and we're squaring it, okay? Okay, and so we get this number. Okay, so let's talk about this. Let's talk about this number that we get, 81.225155625. So if we're not necessarily paying attention to what we're doing and we're just saying, oh, I got a number and now I need to round the number. If I'm just thinking about it that way, I'm going to take this 81.2 something and I'm going to round it down to 81 using the normal rounding rules. But you have to remember that this is a real world problem. This is not just some arbitrary number. This represents an actual thing. This represents how many people we have to have in order to meet these specific requirements. In order to be 99% confident and having a margin of error of 2 ounces, I need to get 81.2 blah, blah, blah people in this survey. Or infants. Well, you can't have 0.2 of a person. And if I round down to 81, I have not met this threshold, right? This is the threshold that we have to meet or hopefully exceed in order to have these particular requirements. So if I just go 81 people, I haven't gotten there yet, right? Like if you picture a number line, like here's 81, here's 82. Well, my threshold is here. It's past 81, but I've only hit 81 if I round down. I haven't met it yet. So what you have to do is you have to round up. Or you can just think of it as go up to the next whole number. because we're talking about people. We're talking about sample sizes of people. So if I need 81.2 people, I better be surveying at least 82 people, because that's the only way to actually meet this threshold. Okay, so that's why your answer is 82, but you'll notice it has 81 as an option. 81 is not your answer, so don't get fooled by that. It's 82. Okay. All right. Okay, number 4, which statistic is the best unbiased estimator for your mean, your population mean? So again, remember your symbols here. So I mean, you can see here it's your sample mean, right? So we have it's the Greek letter mu, and it's your population mean. You guys can't see that. Here we go. Right, that's our population mean. The best unbiased estimator for it is your X bar, which is your sample mean. Okay, and then so just to kind of go over these again, your sigma is your population standard deviation. So S, which is just S, is your sample standard deviation. It's an N. And then your P and your P hat, this is your population proportion. And P hat is your sample proportion. Okay, so you want to make sure that you've got those symbols straight. Okay, this is the best unbiased estimator for this. This is the best unbiased estimator for that. Okay. All right, construct the confidence interval for the population mean, and it gives us a bunch of things. Okay, so we look at what it gave us and we say, all right, do we know our population standard deviation, or is it unknown? They gave it to us, it's right there. So this is what we're doing, okay? If we're doing it in the calculator, we're creating the confidence interval. When we know our population standard deviation, it's going to be stat test z interval. Okay, so let's go ahead and do that in the calculator. We have stat test number 7 z interval, and we're going to plug in what they give us. Okay, first thing it asks for is your population standard deviation. So that's right here, our 0.5. Our X bar is 5.3. Our sample size is 58. And our confidence level is 0.98. And we have the calculator run that for us. And again, we would make sure that we are rounding to 2 decimal places, right? This is a fill in the blank, not a multiple choice. So make sure that you're rounding to the correct number of decimal places. Okay. All right. You are given the sample mean and the population standard deviation. Use this information to construct the 90 and the 95% confidence intervals for the population mean. Interpret the results and compare the widths of the confidence intervals. Okay, so let's label these. For a random sample of 40 business days, okay, N is 40, the mean closing price of a certain stock was this number. So that's the sample mean, right? 117.61. Assume the population standard deviation is 10.23. Okay, so they want us to construct both the 90 and the 95% confidence interval. So we're going to do that on our calculator. Again, we know to find the confidence interval when we know our population standard deviation, stat test the number 7 z interval. Okay, stat test number 7's the interval. And we're going to plug in what we know. Our population standard deviation is 10.23. Our sample mean is 117.61. And our sample size is 40. And our confidence level, first they want us to find the 90% confidence level. So I'm going to go 0.9 or 0.90. Okay, so that's how we're getting these numbers, right? That we can say with 90% confidence that the true population mean is between 114.95 and 120.27. Okay, all right, so now we need to do the 95% confidence interval. Okay, so we're going to go back to stat test number 7, and everything's going to stay the same except we're going to change this to 0.95. Okay, so that's how we're getting this answer. Slightly different, 114.44, 120.78. Okay, so now they want us to say which interval is wider. So I know that we're dealing with decimals here, but if you kind of picture what's happening on the number line, okay, if I have let me pull that down lower. We're going to need to write on both sides here. So 114.95, and this is not to scale, 120.27. Okay, so from here to here is the 90% confidence level. Okay, 114.95 to 120.27. Okay, so now I need to say, well, where in relation to these numbers is 114.44? Where is 0.44 in relation to 0.95? Well, that's a lower number, right? Would you rather be given $44 or $95? 95 is higher than 44, right? So 114.44 is to the left. Again, this is not to scale, but it's to the left. This is 114.44. Okay, so now we're going to compare these. Where is 120.78 in relation to 120.27? This is a higher number than this, right? I'd rather have $78 than $27. It's higher, it's to the right, again, not to scale. So this number is the 120.78. So this was our 95% confidence level, okay? So if we only need to be 90% confident, we've got, I'm not going to call it narrow, but we've got this interval. But if we need to be more confident, then we have to widen our net, right? We have to widen our confidence interval. Right? You've heard that phrase, widen the net, before. Sorry, my computer is doing weird things. Okay. So first thing they say is which interval is wider? The 95% confidence interval is wider. All other things being equal, if you increase your confidence level, you are going to end up widening your interval if everything else stays equal. Okay, so now they want you to interpret that. So you can be 90, we kind of already said this, you can be 90% confident that the population mean price of the stock is between 114.95 and 120.27. And you can be 95% confident that the population mean price of the stock is between these bounds. And you would give the numbers. Okay, but what they're wanting you to see here is that all other things being equal, if you increase your confidence level, if you want to be more confident, you better widen your net, right? Okay. All right, number 7, so very similar, you're given the sample mean and the population standard deviation, use it to construct the 90 and 95, interpret the results, compare the widths. Okay, so let's go through, let's label everything we've got. So a random sample of 36 months, okay. N is 36. The mean number of tornadoes per month during that sample was 97. And then we have to assume that the population standard deviation is 112. Okay. All right, so same thing as before. Again, if you need to refer back to your handy dandy chart here, we know our population standard deviation, so we're going to go stat, test, z-interval. Okay. Stat, test, z-interval. Going to plug in what we know. Okay, population standard deviation, we were told that was 112. Sample mean, that's 97. Sample size, that's 36. Okay, the first confidence level we're doing is 0.9. Okay, so that's how we're getting these numbers. Again, if we round to what they tell us to round to 2 decimals. Okay. Now we're going to do the same thing, but with a 95% confidence level. Okay, so we've got our numbers here. Okay, so again, which interval is wider? So if you're having trouble seeing which interval is wider, go ahead and plot all these numbers on a number line. So 66.3 to 127.7. This is our 90% confidence level. Where is 60.41 in relation to 60.30? Well, this one is, oh, I was like, wait a minute, what? No, because I was looking at the 66. This is 60. 60 compared to 66. It's down here, right? 60.41. Okay, now let's look at 133 compared to 127. Well, this is more. 133 is more than 127. So it's to the right of 127, 133.59. Right, so from here to here is our 95% confidence level. If we only want to be 90% confident, this is our interval. If we want to be more confident, if we want to be 95% confident, we need to widen our net. It widens our interval. Okay, which interval is wider? The higher percentage confidence interval. All other things being equal, if you increase your confidence level, you're going to widen your net. And then they want you to, interpret that. So we're saying that we can say with 90% confidence that the population mean number of tornadoes is between these bounds, and we can say with 95% confidence that the true population mean number is between these bounds. Okay. Okay, so if all other quantities remain the same, how does the indicated change affect the width of the confidence interval? So that's what they've been talking about these last few problems. Now they're just kind of putting it together and having you think about other aspects as well. So an increase in the level of confidence is going to widen the confidence interval, right? We have to widen our net if we need to be more confident that we're going to actually get the value that is the true population parameter. Okay, how does an increase in the sample size affect the width of the confidence interval? So we've talked before about how, you need to have a sample size of 30 or more. If you don't, well, then you better be normally distributed, right? So the more the more samples you have, the larger your N is, the less your interval is going to be. So first of all, how are they wording it? Narrow. It's going to be more narrow. It's going to be smaller. It's going to narrow the confidence interval, because keep in mind that, and we talked about this with like when we were doing probabilities with like cards and dice and stuff like that. Like if you flip a coin one time, you've got a 50-50 chance of landing on heads or tails, right? Well, let's say you flip a coin 5 times. You're not going to get exactly 2.5 times heads and 2.5 times tails. It doesn't work like that. Okay, so let's pick an even number. What if we flip it 10 times? Well, you're probably not going to get exactly 5 heads and 5 tails. If maybe you're going to get 70-30, something like that. If you flip it 50 times, that percentage is going to get a little closer to 50-50. If you flip it 75 times, it's going to get even closer. If you flip it 7,500 times, it's going to get even closer. The higher your sample size, the closer you get to the true, in this case, population parameter. Okay. Ideally, you would do it as many times as your population is. So if you're talking about a population of, I don't know, let's say we talk about the population of, I don't know, the number of students on the Palm Coast campus, because that's where I'm at on Tuesdays. I don't know what that number is. Let's say that it's 2,000 people. I could be way off there. But let's say I'm talking about, population of students at the Palm Coast campus, 2,000 people. Well, if I'm going to take a sample of them, maybe I only take a sample of 50 of them. Okay. So next time I decide I'm going to take a bigger sample. I'm going to take a sample of 500 of them. I've just increased my sample size. I've gotten closer to sampling the whole population. So my confidence interval is going to be narrower because I'm more targeted, right? Okay, I think you guys are getting the idea. All right, and then the last one, the increase in the population standard deviation. How will that affect the width? So it's going to widen it. So if there is a lot of deviation from the mean, then you are going to have a wider confidence interval, right? So if you have people kind of all over the place, let's say, I don't know, we're doing age or something. If we've got people that are 3 years old and we've got people that are 100 years old, and there's a lot of deviation from the mean, maybe the mean is, I don't know, 25. Maybe we're looking at ages of college students. There's there's going to be some deviation there, right? We've got students that are 40. I've worked with a student who was 80 before. I think our youngest students are, in their mid-teens, maybe they're dual enrolled. So we've got some deviation. But if I have maybe a different, like, well, that's kind of a bad example, but I was going to say a different population. Maybe we're talking about a population of high school students. There's not going to be as much deviation from the mean, because most high school students, you're in there for 4 years, maybe 5, depending on what's going on. So there's not going to be a ton of deviation, but in college, you've got a wider deviation. That's going to be widening a confidence interval. Okay. All right. Okay, number 9, construct a 95% confidence interval for the population mean. Assume it has a normal distribution. A random sample of 16 fluorescent light bulbs has a mean life of 645 hours with a standard deviation of 31. Okay, so if we go through and we label what they gave us, we have a confidence level 0.95. Sorry, let me adjust got too many wires here. They're all over the place. Okay. Okay, confidence level of 95%. Then we have this sample of 16 fluorescent light bulbs, which, by the way, they told us it is normally distributed. So it's okay that it's such a small sample, because that sample is, it's normally distributed. Or I'm sorry, the population is normally distributed. But that sample had a mean life of 645 hours, and that sample had a standard deviation of 31 hours. So they just gave us a sample standard deviation, not a population standard deviation. Okay, so we're dealing with this scenario, right? So this is the first one of these that we've done, because we don't know our population standard deviation. That means we're going to have to find a T alpha halves, a t-score. Okay, so just like before, we're going to do this fully by hand. I am going to show you how to find your T alpha halves on the calculator. To be honest, I think sometimes it's easier to just find your T alpha halves by hand, but I'll also show you how to find it on the calculator so that we can then plug it into our error formula so that we can then create our confidence interval. Once we do it by hand and then partially in the calculator, finding that in the calculator. Then I'm going to show you how to do the whole thing in the calculator, right? So finding our confidence interval by hand, we're going to calculate our, in this case, T alpha halves, plug it into E, add and subtract into the E formula, and add and subtract it to find the confidence interval. Okay, so how do we find our T alpha halves? Okay, find the T, specifically the T alpha halves. We can do that by hand or in the calculator. Let's do it by hand. The first thing you need to do is find your what's called degrees of freedom. Okay, so your degrees of freedom is your sample size minus 1. Okay, so in this case, we have 16 minus 1. That's going to be 15. So our degrees of freedom is 15. Now, we are going to look that up in the back of the book in our appendix where it gives us the T values. Okay, now if you can't find that exact degree of freedom, then you always need to go down 1 to find the closest value. Okay, never go up, always go down if they don't have exactly the degree of freedom that you need. Okay, and you're going to find where that degree of freedom and that level of confidence intersect in the table. Okay, because remember, your T alpha halves or your Z alpha halves, it's always based on your confidence level, right? Okay, so let's take a look at, in the back of the book, the T alpha halves. So what's nice about the T distribution table is that it knows you're coming here because you're talking about confidence levels, right? So right there at the top, it tells you, so first of all, over here on the side, it's like, hey, don't forget, for confidence intervals, that's the area in the center, okay? So what was ours again? Our degree of freedom was 15, and our confidence level was 95% or 0.95. Okay, so a confidence level of 0.95, we don't even have to say what's my alpha halves. We can if we want to, but it's giving us that information right off the bat. Just like, hey, look, all you got to tell me is your confidence level. If you want to know your alpha, there it is. If you want to know, or I'm sorry, that's your alpha. If you want to know in each of the tails, I would say don't look at that because you're not worried about that. It's alpha and alpha halves. But anyway, confidence level, 0.95. Degrees of freedom is 15. So I'm going to say, where does 15 intersect with the 0.95 column? That gives me a T alpha halves of 2.131. Okay, 2.131. So my T alpha halves is 2.131. Okay, so great, we just found our T alpha halves. We're going to plug it into our error formula and then add and subtract it to find the confidence interval. Now, real quick, let's go through. If I didn't want to do that in the table, how would I have found that in the calculator? Well, in order to find it in the calculator, you have to actually go ahead and calculate your alpha halves, which is why I think oftentimes for your T-scores, it's faster to do it in the table. Whereas I find that for the Z-scores, it's faster to either look at it to see if it's in the little table that it gives you, because remember, it just flat out gives you a lot of common ones, I think like 5 different common ones. But if it's not there, then for the Z-scores, I find it faster to use the calculator. For the T-scores, I find it faster to use the table. But let's go ahead and do it in the calculator just so that you can see what that looks like. So first of all, you have to actually find your alpha halves. You have to find the area in one tail. So remember, confidence level of 0.95, your alpha is going to be the area in both the tails together, so 1 minus 0.95, so 0.05. So each individual, which is half of alpha, is going to be 0.05 divided by 2, which is 0.025. Right? So now we're going to, we have 0.025. That is the area in one tail. we're going to go to second vars, and we're going to go to 4 inverse t. So if we're looking for a z-score, we go inverse norm. If we're looking for a t-score, we go 4 inverse t. Okay, so we go second vars down to 4 inverse t. And remember, you have to give it the area in one tail. Okay, so the area is 0.025, which again, if you wanted to calculate that, that's, excuse me, it's 1 minus your confidence level divided by 2, right? If you're just like plugging it into the formula. Okay, your degrees of freedom was 15. Remember, that's 1 minus your sample size. And then it calculates it for you. And again, we always take the positive value of that. Okay, so whether we found our T alpha halves in the calculator or by hand, now that we have it, now we're going to plug it into our error formula, right? Okay, so what is our error formula when we don't know our population standard deviation? Here's our error formula. Okay, it's our T alpha halves times our sample standard deviation over the square root of n. So let's plug in everything that we know. We need 2.131 times 31 over the square root of 16. Okay, so let's plug that into our calculator. And we get 16 point, I'll go to 2 decimals here, 52. Okay, right, so our true population mean is our sample statistic, or sample mean, minus our error and plus our error, right? Okay, what's our sample mean? 645. What's our margin of error? 16.52. So 645 plus 16.52. Okay, so in the calculator, 645, whoops, minus 16.52. Okay, and over here, we're going to get 628.48. And then over here, real quick, something I learned earlier this semester, which is cool, is if I want to retype that, but instead of putting subtraction, I want addition, what I can do is I can arrow up to highlight it. And then once it's highlighted, if I hit enter, it'll like copy and paste it. And I can just arrow over and I can change that subtraction to addition, right? So that's a nice little calculator shortcut that I learned earlier this year. Or I could have just typed in 645 plus 16.52. If you have a lot of digits that you have to type in, that can be useful. So we can say with 95% confidence that the true population mean is between this number and this number. Okay. So again, that was done by hand. And then I showed you how to do that partially in the calculator by finding your T alpha halves in the calculator, right? If we take a look at our steps here, when we calculate, so our first step here, this can either be done by hand or in the calculator. And then if you're doing the whole thing by hand, whether you did this or in the calculator, you plug that into your error formula and then you add and subtract it. That's if you're doing it by hand. You can do part of it in the calculator, but this is overall if you're doing it by hand. Okay, so now, what if I wanted to make that whole thing in the calculator? I can do that, right? I can find the confidence interval, the whole confidence interval in the calculator. We don't know our population standard deviation. So instead of stat test Z interval, we're going to do stat test T interval, right? Because this is not a Z score, it's a T score. Okay, so let's see what that looks like. So we go stat, arrow over to tests, and we go down to number 8, T interval. So, I mean, they're right next to each other, right? You see the number 7 and number 8, they're right next to each other. So we go number 8, t interval. And again, just like before, we don't want to use the data. We want to make sure we're using the stats. So make sure that stats is highlighted, and then you go through and you plug everything in. So our sample mean is 645. Our sample standard deviation is 31. Our n, our sample size, is 16, and our confidence level is 0.95. And there it is. And again, if we round to 1 decimal, we're going to get the same numbers that we got when we did it by hand, right? Okay. All right, number 10, construct a 90% confidence interval for the population mean. Assume the population has a normal distribution. In a recent study of 22 eighth graders, so my n is 22, so good thing it's normally distributed, because otherwise I wouldn't be able to use all these formulas because my sample size is less than 30, but it's okay because it's normally distributed. Okay, in a recent study of 22 eighth graders, the mean number in that sample of hours per week that they watched television was 19.6. Okay, so that sample mean was 19.6 with a standard deviation of 5.8. So that's a sample mean of 5.8. Okay. So again, we could do this by hand, but I'm going to go ahead and do it in the calculator. All right, we're going to construct our confidence interval, and I'm going to do it in the calculator. I don't know my population standard deviation. All I know is my sample standard deviation. So this is going to be a t interval, right? Stat test number 8, which is t interval. Okay. So stat test, arrow down, or just select number 8, t interval, and we plug in what we know. Sample mean is 19.6, sample standard deviation is 5.8, n, sample size is 22, confidence level is 0.9 or 0.90, but if you put 0.90, it's just going to change it to 0.9, same thing, and calculate. And they've rounded to 2 decimal places in the answer, so that's what we would do as well. And again, if we were to interpret this, we would say, and also, by the way, I know that they write it like this, but keep in mind what they're actually saying is that the true population mean is between, this lead will be the death of me, is between 17.47 and 21.73, right? That's 2 different ways of writing the same thing, okay? But this is what we're saying. We're saying that we can be 90% confident that the true population mean is between these 2 values, okay? All right. Number 11, construct a 99% confidence interval for the population mean. Assume the population has a normal distribution. Good that it does, because our n is only 19. Group of 19 randomly selected employees has a mean age of 22.4, and that sample had a standard deviation, so that's a sample standard deviation of 3.8 years. Oh, I forgot to write that our confidence level was 99%. So we have a sample standard deviation, not a population standard deviation. So this is going to be a t-test or a t-interval, not a z-interval. Again, we could do this by hand, but I'm just going to do it in the calculator. Stat tests number 8 t-interval. Plug in what we know. So 22.4, 3.8, and 19, and 0.99. Now, I will say that sometimes if I'm going too quickly, when I go to plug my numbers in, instead of actually looking at what it's asking for, I just like go down the list here and I just plug them in that order. Don't do that. Take your time, look at what you're doing. And I mean, you're going to get some weird numbers sometimes if you do that. So you might be able to kind of check yourself and say, hey, does this kind of make sense? Is this even close to the numbers that I'm being given in the answer or as my potential answers? But if you do find that you're doing that a lot, then it might be a good idea to, instead of writing down what they've given you in the order that they give it to you in the problem, you can, before you write down what they give to you, you can do this. You can say, okay, well, I know in the calculator, this is the order that I'm going to have to write things. So you could write it out like that, and you could say, okay, a 99% confidence level. Okay, so that's down here. So I'm going to fill that in. Okay, a group of 19 people. Okay, that's an N. Okay, that's here. That's 19. A mean age of 22.4. That's up here, 22.4. And the standard deviation, 3.8. Right, so you could do it that way. And then you could just kind of go down the list. 22.4, 3.8, 19.99. But that's only if you find that you're accidentally plugging the wrong things in because you're just kind of going in order down the list. All right, but we plug that in. And again, we're getting the same values that they're getting as long as we round to 1 decimal. Okay. Okay, a random sample of 40 college students, go in 40, has a mean earnings, okay, that sample mean is 3120, over the summer months. Assume the population standard deviation of earnings over the summer months for college students is this number. Okay, so that's population standard deviation. And that the distribution of earnings over the summer months for college students is normally distributed. Determine whether a normal distribution or a t-distribution should be used, or whether neither of these can be used to construct a confidence interval. Okay, so they're asking which requirements have been met. Now, I don't think in your chapter that they go into too much detail about what exactly a t-distribution is. I mean, there's a whole deep dive you could do with that. You know, a normal distribution versus a t-distribution. But for the purposes of your chapter, they're really just wanting you to say, okay, well, do I know my population standard deviation or do I not know it? Because that's going to tell me whether I'm using a z-score or a t-score. Z-scores are done on normal distributions, t-scores are done on t-distributions. Okay, so we were given a population standard deviation. It is known, so we have a z-score, which is a normal distribution, not a t-distribution, but a normal distribution. Now, they told us that it was normally distributed, right? And they told us that our sample size was greater than or equal to 30, right? Our sample size was 40. So we do meet the requirements. Sometimes you don't meet the requirements. That does happen in some of the problems that you're given, and you would have had to have said, oh, I can't use either if my sample size was less than 30 and if it wasn't normally distributed, right? Because it needs to be either one of those. So if neither of those is checked out or checked off, then you can't do either. But in this one, we say the population standard deviation is known. Check. It's a simple random sample. Check. Either this or this. What's one of these? Normally distributed, or n is greater than or equal to 30. So I need a check mark in one of these. Doesn't have to be both, but one of them. Well, we actually got a check mark in both of those. So we definitely have a check mark there. So it does meet the requirements. So that's why we can use a norm. So first of all, that's why it's not this. It's not that. And then the reason that we know that it's normal versus t is because if we know our population standard deviation, it's a z-score, which is a normal distribution. If we don't know our population standard deviation, it's a t-score, which is a t-distribution. Okay. A random sample of 15 statistics textbooks has a mean price of 105 with a standard deviation of that sample, so a sample standard deviation of 30.25. Determine whether a normal distribution or a t-distribution should be used, or whether neither of them can be used to construct the confidence interval, and assume the distribution of the textbook prices is not normally distributed. Okay, so first of all, I have a sample standard deviation, not a population standard deviation. So that means we're going to be looking at this column, right? So we're going to say, okay, do we meet all of these requirements? Okay, so population standard deviation is unknown. Yep, check, it's unknown. We have sample instead. Okay, it is a simple random sample. Yep, it is. They told us it was random sample. And then either it's going to be one or the other. Either it's going to be normally distributed, okay, or if it's not, that's fine, as long as our n is greater than or equal to 30. Okay, so they told us specifically that it was not normally distributed. Okay, so it's not normally distributed, so we can't put a check mark there. Well, that's fine as long as we can put a check mark here, except that we can't. We can't put a check mark on either of these because our sample size is not greater than or equal to 30. So that requirement is not being met. And that's why we cannot use either, because we're not meeting the requirements for either. Okay. All right. Construct the indicated confidence interval for the population mean using the t-distribution. So they're sort of reminding you right off the bat, hey, when you have a sample standard deviation, don't forget that's a t-value that you have to find, or a t-distribution. And then assume it's normally distributed. So again, we're going to use stat test number 8, t-interval, to do it in the calculator, as opposed to doing it by hand. You could do it by hand. If you do it by hand, here are your steps. Find your t-alpha halves, either looking at the table or in the calculator. I think the table is faster. Then you plug those values into your E formula. Again, your error formula is this. Then you plug that error in to find your interval. That's if you were doing it by hand. We're going to do it in the calculator because it's much faster to do it in the calculator. So we're going to go stat, test, and then number 8, t-interval, and plug in what we know. So they gave us everything. Okay, so X bar, 12.3, sample mean. Sample standard deviation, 0.93. N is 19, and confidence level is 0.98. Okay, and then we plug in. Again, make sure that you're always taking a look at what they say to round to. Sorry, you couldn't see that, I apologize. Making sure that you're looking at how many decimals that they say to round to. Okay. Right, in a random sample of 22 people, hold on. And 22. The mean commute time to work, so the sample mean, was 34.5 minutes, and the sample standard deviation was 7.1 minutes. Assume it's normally distributed. It's telling you flat out, don't forget you have to use a t-distribution because we have a sample standard deviation, not a population standard deviation, to construct a 95% confidence interval for the population mean. Then they also want you to say specifically what is the margin of error. Okay, so if we were to do this in the calculator, we're going to do it, I mean, kind of both ways here. We can absolutely find our confidence interval super quick, right? We go stat, test, 8, we plug in the values that we know, 34.5, 7.1, N is 22, confidence level is 0.95, and calculate. Okay, so we get that, we plug it in. Okay, but then it wants the margin of error. Now, there's two ways to do this. So if we remind ourselves, the margin of error, there's a whole formula for it. If we were to do it this way by just using the formula, then we would have to first find our T alpha halves, which, okay, maybe we look it up in the table, maybe we use the calculator, and we have to plug this in. Or we could remember the relationship between these numbers that we just found, by the way, right? We found what those numbers are, and the error. It's that the error was being added and subtracted from the sample mean, okay? So what they're wanting you to see is that you don't have to start over from the beginning and go find your T alpha halves and plug it into the error formula. You can just add and subtract your sample mean from these numbers to get the error, okay? So let me show you what I mean by that. We're saying that we took our sample mean and subtracted the error and the sample mean and plus the error, and that's how we got these numbers. So what we're saying is that x bar minus the error is 31.4 and that x bar plus the error is 37.6. We don't know the error, but we do know the sample mean. Like we were given that, right? That's a known value. 34.5 minus the error is this number here, right? That's this number here. So this is just an equation that we can solve. Same thing over here, right? I have 34.5 plus the error is equal to this number, right? These are our two numbers that are represented here, okay? So x bar minus the error is this. X bar plus the error is this. Right? You see how that's related? So what I can do is I can solve either one of these equations to get the error. And it's going to be less work than if I had started from the beginning, found my T alpha halves, plugged it into the formula to find my margin of error. Now I'm going to use this one just because I know that negatives tend to frighten people. So that would be my suggestion. If you get a problem like this on the test, if you're not super comfortable with negative numbers, then just use this formula, okay? Or this one, the one where you've added the error as opposed to subtracted the error. So we're going to solve this equation for E. So it might have been a while since some of you have done algebra. So remember that to solve an equation, you get everything that has the variable in it on one side and you get everything that doesn't have the variable on the other. So this is just a number, it's got to go to the other side. So to move it, I have to subtract it because it's positive. So the opposite of adding a 34.5 or having a positive 34.5 is to subtract it. Adding and subtracting the same number cancel each other out. And on this side of the equation, I get just the error. And then this, I can just plug into the calculator. 37.6 minus 34.5. And I get that the margin of error is 3.1. And if we wanted to prove to ourselves that that was right, we could plug it back in here and say, if I add and subtract 3.1 from my sample mean, will I really get these values, right? So first of all, that's all the work that you have to do. But if you wanted to check it, you could say 34.5 minus 3.1 and 34.5 plus 3.1. Do I really get 31.4 and 37.6 for these numbers, right? So 34.5 minus 3.1. Yeah, I got 31.4. Okay. Now what if I add it? Yeah, I get the same thing. Okay. So that's why we have 3.1. And then again, they want us to interpret the results. So we can say with 95% confidence that the true population mean is between those two numbers. And they're always specifying the population mean of what? Of the commute time is between the bounds of the confidence interval. Okay. All right, 16. Use the standard normal distribution or the t-distribution. So they're saying, hey, you got to figure out which one it is this time to construct a 95% confidence interval. That's, whoops, I was about to write n. That's our confidence level is 95. For the population mean, justify your decision. If neither can be used, explain why and interpret the results. Okay, random sample of 11 mortgage institutions. The mean of that sample was 3.52%, and the standard deviation of that sample was 0.41%. Assume that the rates are normally distributed. Okay, it's a good thing that they're normally distributed because our sample size is less than 30. So it has to be normally distributed in order for us to be able to do anything. So we know that because we have a sample standard deviation, not a population standard deviation, that we have to use a t-distribution. Okay. All right, so we're going to use the calculator for this. So we're going to go stat, test, number 8, t-interval. We're going to plug in what we have. You see the whole thing there. All right, so our sample mean, our sample standard deviation, our sample size, and our confidence level. Okay, so again, if we go to 2 decimal places there, then that's how we're getting those numbers, right? 3.7954, that rounds to 3.80 if we go to 2 decimal places. And then again, interpreting the results, we can say with 95% confidence that the true population mean interest rate is between 3.24 and 3.8%. Okay. So it might look like a lot, but once you label everything and once you know what situation you have and find the confidence interval, if you know which one of these you have, it's not, hopefully not too scary. Okay. A survey of 100 fatal accidents, that's an N, showed that 32 were alcohol related. Find the point estimate for P, the population proportion of accidents that were alcohol related. Okay, so on one of the previous questions, it was asking what is the best best unbiased estimate for the population parameter? It's the sample statistic, right? So for the population mean, it's the sample mean. For the population proportion, it's going to be the sample proportion. So remember, your sample proportion is your X over your N, right? The number of successes over your sample size. Okay, now when we say successes, that does not necessarily mean a positive thing or a good thing, because in this case, the number of successes, or what we talk about as a success, is that a fatal accident was alcohol related. Okay, that is our X is 32. That's the number of fatal accidents that were alcohol related. So we can find our P hat, which is the best point estimate for our P. Our sample proportion is the best point estimate for your population proportion. Finding your sample proportion is putting your X over your N. Okay, so our X is 32, our N is 100. You can either plug that into the calculator or you can notice that you're dividing by 100, so you can just move your decimal to the left 2 places, or you can see that this is like 32%, right? Either way, that's how they're getting the 0.32. Okay. Okay, a survey of 2,090 golfers, that's an N, showed that 302 of them are left-handed. Well, that's an X value. Find a point estimate, so same thing here, for P, the population proportion of golfers that are left-handed. Now, just a side note here, if they had said that are right-handed, then you would just take the complement of that, right? Where you would say, you would do, if all 2,090, they're either going to be left or right-handed. So if 302 of them are left, we would do 302 subtracted from 2090. That would give us how many of them are right-handed. From what I've seen, you guys are not given problems like that in the online class. If you take the face-to-face class, I think they do give you problems like that, where they tell you, oh, this is how many left-handed, and then they ask you about how many right-handed. So I haven't yet seen one in the online classes that they do that, but just be aware that they might. I don't think they will. They might. And if you take it face-to-face, they will. Okay, so again, the best point estimate of the population proportion is the sample proportion, and the sample proportion is the X over the N. So we're going to put our X, which is 302, over our N, which is 2090. So we're going to plug that into the calculator to get that decimal of 0.144. Okay. All right. A researcher at a major hospital wishes to estimate the proportion of the adult population of the United States that has high blood pressure. How large a sample is needed in order to be 98% confident that the sample proportion will not differ from the true proportion by more than 2%. So my margin of error here is 2%. Let me get out my formulas here. Okay. So we're finding a sample size, right? So this is the formula we're going to be using. Let's write that down real quick. Okay. So we didn't write down a p hat, right? But that's okay, because when p hat is unknown, assume that p hat is 0.5. Okay. So we're going to assume that p hat is 0.5. Okay. All right. So when we do this, we're going to need to find our z alpha halves, right? And we can either do that in the calculator, or we can do it um, on the table, right? So I didn't put in my error, sorry, 2%. So let's go ahead, got too many papers sitting around here, and find our z alpha halves in the calculator, right? Let's try and do this as much in the calculator as we can to save ourselves time. So we want to find our z alpha halves, okay? In the calculator, second vars, inverse norm, the area is the confidence level. We make sure that the tail is the center, and we leave these as 0 and 1. Okay. So we're going to say second vars, we're going to go inverse norm. The area is our confidence level. Leave these as 0 and 1. Make sure the tail is in the center. And then it's going to give us our values. Again, it's giving you a negative and a positive because it's giving you that if this is 0.98, then alpha is 1 minus 0.98, so 0.02. So alpha halves is 0.01. right? The area in each of those tails individually is 0.01. It's giving us a negative and a positive z-score because it's giving us this z-score and this z-score, right? Okay. All right, so we've got a z-score of 2.32. Or sorry, 2.32. But also, so I've done this problem before, and I want to show you that in the back of the book, if you look that up, a confidence level of 98%, the area in one of the tails is 0.01. So that's going to be, we've done this one before, right? We did the 0.01, so that's negative 2.33 because that's as close as we can get. So 2.33 is different than 2.32. So if you look it up in the back of the book, you're going to get a z alpha halves of 2.33. But if you do it in the calculator, you're going to get a number that when you round it, it rounds. Oh, no, it does round to 3.3. Okay, I don't know which one I was looking at there. I was looking at one that rounded to something different. Oh, I know what it was. It was because previously I went to 3 decimal places rather than 2 decimal places. Okay, so either way, we're getting a z alpha halves of 2.33. Let's plug everything in. We have to have all of these to plug in. We have our p hat. We can easily find our q hat because it is the complement of p hat. Remember, we talked about that at the beginning, that if p hat is 0.5, q hat is also going to be 0.5. We have our z alpha halves, which we found based on our confidence level. We've got our margin of error, which they said 2%. I don't think I talked about that. When they're saying 2%, we need to change that to a decimal. Our margin of error is 0.02. And then we're going to plug it in and square it. Okay, so I'm going to be a little excessive with my parentheses just because we have so much going on here. 0.5 times 0.5 times 2.33 over 0.02, all to the second power. Okay. All right. Okay. So again, we're getting a number that isn't just a random arbitrary number. This is a number that represents how many people we need, the threshold of people that we need in order to be 98% confident and to have a margin of error of no more than 2%. So if we don't meet this threshold, then we're not working within these confines. So I can't have 3,393 people because I haven't yet met the threshold. This is just over that number, right? Again, think of it on the number line, 3,393, 3,394. This is just a little bit after 0.06. It's 6% of the way through, okay? So if I only go up to here, I haven't actually crossed the threshold, and you have to meet or cross the threshold. So remember the rule, go up 1 to the next whole number. So that's how they're getting 3,394. And then just to show you real quick what I was talking about with the rounding here, if I had gone to 3 decimal places, so 2.326, so I would have had 0.5 times 0.5 times 2.326 over 0.02 square. And you can see I'm getting a bit of a different number there, right? So if you get a number that you're not seeing, I mean, yeah, it's close to that, but it's not that, even if you use the correct rounding. I don't like to say rounding, I like to say just go up. But even with using that, that's not that. So if you get something like that, then go back and adjust your z-score to just go to 2 decimals. Okay. You might run into that from time to time. Okay, a researcher wishes to, oh, sorry, hold on. Here at the Flagler Palm Coast campus, the desk here is not quite big enough to fit everything in, so I'm constantly knocking stuff over. Okay, a researcher wishes to estimate the number of households with 2 cars. How large a sample, so again, we're going to find our N, right? What is our sample size? How large a sample is needed in order to be 98% confident, so our confidence level is 98, that the sample proportion will not differ from the true proportion by more than 4%. Okay, so that's our margin of error is 4%. Okay, but then they tell us that a previous study indicates that the proportion of households with 2 cars is 19%. So a previous study gave us a p-hat of 0.19. Okay, so now when we go to use our formula, so we have p-hat and q-hat and c alpha halves over the error squared. So we have been given p-hat. So we're not assuming that this is 0.5. So again, our q-hat is 1 minus our p-hat, which is 1 minus 0.19, which is what, 0.81, right? Okay, so again, we need to find our z alpha halves. So that is going to be, again, if I do that in the calculator, to find our z alpha halves in the calculator, we're going to do second vars. The area, or number 3, inverse norm, the area is our confidence level, okay? So we're going to do in our calculator, we're going to do second vars, number 3, inverse norm. The area is the confidence level, which is the 0.98. We leave our 0 and 1 and we say paste. So again, this is that same z alpha halves. Let's go to 2 decimal places and then plug everything in. Okay, so we have 0.19, that's our p-hat. Our q-hat is 0.81. Oh, you know what I forgot to do? So first of all, we know that we can do this because they gave us, oh, never mind. I'm thinking of a different problem. Anyway, okay, so we plug everything in. Our error was 0.04. Okay, so we're going to plug this all in. Okay, and again, 522, 1923188. What do we do with that? We go up to the next whole number because I can't have 0.19 of a person, and the only way to guarantee that I've met or exceeded that threshold is to go up to the next whole number. Okay, let P be the population proportion for the following condition. Find the point estimates for P and Q. So remember the point estimate is the P hat, which is X over N, and then the Q hat, which is the complement of P hat. Okay, a study of that many adults, that's our N, 4237, from country A, in a study of those adults from a particular country, that many think that the mainstream media is more interested in making money than telling the truth. Okay, so that's our X is 2486. So our P hat is X over N. So that's going to be 2486 over 4237. Okay. We plug that into the calculator. And oops, I did subtraction instead of division. All right, so rounding to 3 decimal places, we get that number. Okay, now there's 2 different ways to find the Q hat. The easiest way is going to be just doing 1 minus that. So I can do 1 minus, and then down here, where it says answer, I can say, yeah, please take the answer from the previous one and plug it in. So I can go second answer, and it takes the answer that I previously had, and I can get my 0.413. Okay. Another way to do it, I mean, that's going to be the fastest way. But if you wanted to, you could say, all right, well, if there's 2486 that say that they do think that, how many don't think that? Well, if this is the whole sample size, they're either thinking it or they're not thinking it. So we can just subtract it to get the other one. So if I do 4237 minus 2486, this is how many people don't think that. So this number of people do think mainstream media is more interested in making money than telling the truth. This is how many people don't think the mainstream media is more interested in making money than telling the truth. And we can prove that to ourselves by saying, okay, our Q hat is going to be that number over our sample, right? So 1751 divided by 4237. And sure enough, we get the same decimal. So just keep that in mind. Lots of different ways to kind of look through things. Okay. In a survey of this many adults, this many say they believe in UFOs. Construct a 99% confidence interval for the population proportion of adults who believe in UFOs. Okay, so again, we can either do it by hand or we can do it in the calculator. Okay. If we do it by hand, we're going to find our margin of error, which is going to be our Z alpha halves times P hat times Q hat over the square root of N. We need to make sure that our N times P hat and N times Q hat is greater than or equal to 5. So we're going to check that real quick. Then we're going to go through, we're going to do this by hand, and then we're going to do it in the calculator because I want to do at least one of each type of problem by hand. Okay, so first of all, let's make sure that our P hat times N is greater than or equal to 5. Okay, well, in order to do that, I need to know what my P hat is. Well, P hat is X over N. So we have 705 over 2266. Okay, so that's 0.311. Okay, so that's our P hat. So 0.311 times N, is that greater than or equal to 5? Yeah, we're good. What about our Q hat? Q hat is 1 minus P hat. Well, our Q hat, or I'm sorry, our P hat was 0.3111. So our Q hat is 0.6889. So Q hat times N. So we take that times N. Is that greater than or equal to 5? Yeah, we're good. All right, so we have met the requirements, right? You always need to make sure that you've met the requirements down here, okay? We're going to find our Z alpha halves so that we can plug it into our error formula so that we can plug our error into either, well, to both add and subtract from our sample proportion to create our interval, okay? All right, so our Z alpha halves is based on our confidence level, which was 99%. Okay. This is the Z alpha halves, not a T. So in the back of the book here, the Z alpha halves of a confidence level, can you see that, of 0.99 is going to be 2.575. Okay, so now we're going to plug all of the information into our error formula, which is Z alpha halves times P hat, which was, I'm going to go ahead and use the fractions here. Just so that I'm not rounding as I go through and do this. So if 705 of these do believe that, then 1561 of them don't. So that's P hat times Q hat over, oh, I'm sorry, I'm getting ahead of myself here. I was just going to write the formula out real quick for us. Well, here, I'll write it over here. I'm just copying this down from our sheet, right? Over square root of n. Okay. And then our Z alpha halves was 2.575. And then over n, which is 2266. So now you're not always going to have like fractions within fractions underneath roots. You can use the decimal there if you want to. I mean, ideally, you're not doing this by hand. You're going to do the whole thing in the calculator. You're going to have the calculator create the confidence interval for you. But just to show what it would look like if we did it by hand, that's why I'm going through. So I'm going to be a little excessive with my parentheses just to make sure that the calculator is doing the order of operations correctly here, okay? So I have 2.575 times the square root of, okay, so underneath this, I'm going to have a parenthesis for the numerator, and I'm going to have a parenthesis for each of the fractions inside of it. Okay. Okay. So we're getting an error of 0.025. Okay. Now that I have the error, I can plug it in and say that my true population proportion is my sample proportion plus my error, my sample proportion minus my error. So my sample proportion was, I'm going to continue to use this fraction just so that I'm not rounding as much kind of throughout. Oops. We just found the error. That's what we're plugging in, 0.025. Okay. Okay, so we're getting 0.286. And then I'm going to do that thing again where I go up, I highlight, oh, sorry, you couldn't see half the problem there. I apologize. Highlight, I hit enter, and then I'm just going to go back and say, okay, instead of subtracting it, I want you to add it. And then we're going to go to 3 decimals. Okay, so that's all the work I would have to do if I did this by hand. I mean, either way, we have to do the thing where we find P hat and Q hat and make sure that they're greater than or equal to 5. But besides that, we had to do all that work by hand, okay? Or we do it in the calculator, right? We can find our confidence interval in the calculator. We're going to go to stat tests, and then we're going to go all the way down to A, or alpha, 1 prop z int. Right? This is a proportion, and it's a z interval. Okay? It's a proportion, it's a z interval. So stat tests, and then go down to A. So we go stat tests. Now, when we were dealing with means, it was either our z interval or our t interval, right? But now we have to go down even farther. So I'm going to go down, 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 all the way to A, or alpha. Now you can get to that a couple of ways. You can go down a whole bunch, you can go up and kind of start back at the bottom, or just like before, like if we wanted to do 8, we could just press 8. Oh, you can't see my hand. You could just press 8. You can also just go directly to the A, like select it directly. If you see on your, I mean on mine, yours might be a different color. There's a yellow letter on top of each of the buttons. So on top of the apps button is a B, on top of the program button is a C, on top of the VARs button, well, there's not one there, on top of the inverse or x to the -1 is a D, so on and so forth. The A is above the math button. So I can either hit enter or I can hit alpha math and it will automatically select A. Okay, but either way you do it, go to A, 1 prop z int. Okay, so now we're going to plug everything in. So we have, oh, last time I was in this menu, I was doing this problem. So our X value is our 705, right? Our N is our 2266, and our confidence level is, oh, this must have been a different problem because this is 99%. And there we go. If we round each of those to 3 decimals, there it is. So you look at the amount of work that we did here, versus even with me explaining the menus and everything, it took significantly less time to do it in the calculator, right? Okay, so we can say with 99% confidence that the true population proportion lies between those two values. All right, a researcher wishes to estimate with 99% confidence, so our confidence level is 0.99. The population proportion of adults who support labeling legislation for genetically modified organisms. Her estimate must be accurate within 5% of the true proportion. So that's our margin of error is 5%, 0.05. So when you're doing margin of error, you need to have, if it's a percentage, you need to write it as a decimal. Okay, so for part A, it says no preliminary estimate is available. Go ahead and find your minimum sample size needed. Okay, so finding our N. So we've done one like this, right? Our N, our sample size formula. We've done this one before, right? We need to have a Z alpha halves. So we need to find the Z alpha halves that corresponds to our confidence level of 0.99. Conveniently, the textbook does provide that. 0.99 is going to be 2.575. Okay. So our Z alpha halves is 2.575. So I'm just going to jot down our formula real quick again, right? P hat times Q hat, whoops, not equals, times Z alpha halves over the margin of error squared. Okay, so we have almost everything we need, but we still need our P hat and our Q hat. We don't have that. They said no preliminary estimate is available, but that's okay because when we don't have it, we assume that P hat is 0.5, which by default means that our Q hat is also 0.5. Okay. All right, our Z alpha halves was 2.575. Our margin of error is 0.05, and we're going to square it. Okay, so we're going to plug this into the calculator. Okay, So, okay, so you remember when I said earlier, um, if you're not getting the number that you want, take your z-score and go to just 2 decimal places. So let's go ahead and do that here, because you'll notice that they're saying that it's 666, and I got a slightly different number. Uh, right. Now, you might want to check with your instructor and see if like if you do use the 575, because that's what the book gives you, or that's what the appendix gives you, if it'll still accept that answer. You might want to check with them on that. Otherwise, just go to 2 decimal places for your z-score. Okay, so we're getting 665.64. But again, this is a sample size. This is the number of people that we're talking about. I can't have 0.64 of a person, but if I just have 665, I don't have enough people. I haven't met the threshold, so I have to go up to 666. Okay, so then part B, find the minimum sample size needed if we have a prior study, using a prior study that found that 74% of the respondents said that they support labeling the legislation for GMOs. So now we have a previous study, so we have a p-hat. The p-hat is, this is part B, the p-hat is 0.74, so the q-hat is going to be 1 minus that, so 0.26. Plug it into your calculator, 1 minus 0.74 to get 0.26. So now when we go to plug this in, we're not just assuming 0.5, we have a previous study that gives us a little bit more information, right? We can be a little bit more accurate now. Okay, so we're going to have 0.74 times 0.26, and we get 512 point something. We don't care what the something is. All we care about is that I got more than 512, so I have to go up to 513. Okay. All right. And then C, compare the results. So if I had no previous study to rely on, I needed 666 people. But if I have only one previous study that gives me some point of reference that I can use for a p-hat and a q-hat, I've just drastically reduced the sample size that's needed to stay 99% confident and to keep this margin of error of just 5%. Okay? Do you see that relationship there? And that's what they're asking us about. How do they compare? Having an estimate of the population proportion reduces the minimum sample size needed. Now, in an ideal world, your sample size, like you would just get as many people as you could, right? I mean, this is the minimum that you need. You're going to want more than that. You're definitely going to want more than that, but that's the minimum that you would have to have. Okay. All right. And last problem, last but not least, they wish to a researcher wishes to estimate with 90% confidence. That's our confidence level, 0.9 or 0.90, population proportion of families who eat fast food at least once per week. Okay, her estimate must be accurate within 2% of the population proportion. Okay, so our margin of error is 2%, 0.02. For A, no preliminary estimate is available. Find the minimum sample size needed. Okay, so again, we're going to have to assume a 0.5 for our p-hat and our q-hat. Okay, but first thing is, because we're going to be plugging into our sample size formula, we're going to need our p-hat, we're going to need a q-hat, we're going to need a z alpha halves, right? So let's go ahead and get all those things. We know we're going to be 0.5 for the p-hat and the q-hat. For the z alpha halves, remember your z-score or your t-score is reliant upon your confidence level. We have a confidence level of 90%. So thankfully, The table in the back says that if you have a confidence level of 0.9, your Z alpha halves is 1.645. I'm just going to go ahead and go to 2 decimals here. So 1.65. So I'm going to say that my Z alpha halves is 1.65. And we're going to say that our, whoops, I meant to write the P first. We're going to say that our P hat is 0.5 and our Q hat is 0.5, because we have to assume that if we don't have them. Okay, so we're going to plug these in. P hat is 0.5, assumed to be, Q hat is assumed to be 0.5, Z alpha halves is 1.65, margin of error is 0.02, and we square it. I know that if I get thicker lead, it won't break as often, but I don't like the way that the thicker lead writes. Okay. All right. So, so let's go 645. And see if that makes a difference. Okay. All right. Okay, so that makes me think that it'll accept either answer, whether you use the one that it gives you in your appendix or whether you round to 2 decimals. Because on the last one, we had to round what the appendix gave us, and on this one, they don't want us to round what the appendix gave us. So if you ever get a question wrong on the homework or on the test and you think it's because of a rounding thing like that, just bring it up to your professor and just say, hey, look, this is the work that I did. This is where I rounded or didn't round, and see if they'll give you the credit. But I'm thinking that the software program will take either one. Okay. So not rounding in this case, using the exact value in the chart, we get an N of 1691 and some change, right? 0.265, blah, 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 blah. Well, anyway, we keep going. This is the number of people, so we have to go up to the next value, 1692. That's how we have to go up. That's how we get 1692. Okay, but then, like with the last problem, now we have a prior study. We uncovered a prior study, and that prior study found that 22% of those respondents said that they ate it 4 to 6 times per week. We're looking for at least once per week, so that works, so we're going to use that because that is at least once. 4 to 6 is at least once. So now, so we have our confidence level of 0.9, 0.9. We've got our margin of error of 0.02. We've got our Z alpha halves of 1.645, but now we have a P hat of 0.22, which means we have a Q hat of 0.78, which is the complement of that, right? We get that by saying what's 1 minus 0.22. That's how we're getting the 0.78. Okay, so now with additional information, with a prior study that's related, that gives us a point of reference, some context. Let's see how that affects our minimum sample size that we need. And we get this number, which we have to go up to the next whole number, not because that's an 8, but because these are people. And we need a whole number of people that meets or exceeds that threshold. Okay, so that's how we get that. So again, they're having you compare them. Having an estimate of the population proportion reduces the minimum sample size needed. Okay, so I hope what you've taken away from this is that there are certain instances where using your calculator is going to be faster. And then there are some instances where using The tables in the book will be faster. I will be providing this sheet here as a PDF in the email that I send out. As always, don't hesitate to reach out to me or go to any of the academic support centers to get some help. Don't forget that the Academic Support Center on the Daytona campus in Building 115, so that's the one that's inside the library, it's open on Saturdays. It's open from 8 a.m. to 4 p.m. on Saturdays. And we've got math people there staffing it on Saturdays. Also, if it's after hours, so if your local ASC is closed, we have the online chat that goes from 8 a.m. to 7:30 p.m. Monday through Thursday, and 8 a.m. to 5 p.m. on Fridays. So you can go online and get the virtual chat. And the virtual chat, you're talking to a human. You're talking to me or to any of the other learning specialists. We're the ones that man the chat. So take advantage of those resources. Also, your professor is a great resource. They want you to reach out to them, ask questions, get clarification. If you're able to go to their office hours, that's great. I know with online classes, you're probably taking it because you work, and so it's easier for you to do the class online rather than go in person. But there might be some times where your free time overlaps with their office hours, so don't hesitate to make use of that. As always, I'll be including my hours of where I am on what days in the email that I send out if you want to come see me in person. Okay, I hope this was helpful. And good luck on your exam.